Welcome to the first linear algebra actual math talk. So in this little 15-minute or whatever time, I'll give you an introduction to what we're going to study in the course, a little bit of material about how it works, and prepare you for Friday's class. So I'd like you to watch this before Friday, and Friday's class will have a worksheet containing some of these ideas and also a homework assignment. So linear algebra is about two things and sort of two things only: linear equations and linear functions. And I'd like to talk a little bit about each one of those. So one of the first things I'd like you to be able to do is to recognize them. Recognizing a linear equation is important. So usually at this time in class, I will, if I'm meeting in person, I will ask someone to give me a linear equation. So I would say, could somebody give me a linear equation?
Yeah, I can.
Snow, you came early. Where's Ohm?
He's late. He's always late.
I know he's often late, but did he know about this?
Yes, I told him like usual he's late.
This is Snow. She'll be helping somewhat during the term. We have another, Ohm is also around. He's also one of the creatures that I live with. But Snow, what would be a linear equation?
Like 2x plus 1.
Well, yeah, almost, but it's not an equation. So if you would have said y equals 2x plus 1,
That's what I meant.
yeah, I thought that's what you meant. Then yes, this is a linear equation, and you can tell it's a linear equation because all the variables are to the first power if they show up in the equation, and the only operations are plus and minus, and this scaling is possible, so we can double or triple any of the variables multiplying by a number, and then you can add a constant. So adding constants, subtracting constants, scaling, only operations are addition and subtraction, and it's got an equal sign. That's a linear equation. Has two variables. So we'll be interested in graphing these, and surely you have vast experience in this. Usually the graph lies in a Cartesian equation where you plot the domain first of all, and then the range is plotted vertically. And the equation itself, when you graph it, looks a lot like one of the axes. You could pick either one. I'll pick the x-axis because we're going to talk about functions later, but it looks like a number line. But this, the graph of this, geometrically looks like a number line, but it's not placed in the same place. It has a slope of 2, and it has an intercept of 1. So there is the graph, slope of 2, intercept of 1. So I'd like you to be able to recognize these linear equations both by their equation themselves, and recognize that the graph is flat and in one dimension less. So the graph of this will be flat, one-dimensional. It'll look like a real number line. Now, if we tried one dimension less than this, so we have a linear equation, so it's got an equal sign, and it's got, say, only one variable, then we could simplify this and get x equal 2. So x equal 2 is a single position on the real number line. So the real number line is a line, a flat line. This is one dimension less, this is 0-dimensional, and this is just a single point. So linear equations with only one variable. We can also have linear equations with many variables, but we could have a linear equation with 3 variables, like 3x1 plus 2x2 plus x3 equals 6. So this is a linear equation. It's got three variables. It only uses the appropriate operations of plus, minus, equal sign, and all of the exponents that appear are 1. And the home for this, the home for the graph, is three-dimensional space. This counts the number of variables that you need to graph this thing. In a Cartesian graph, these coordinate axes, all one-dimensional, are put perpendicular to each other. And this graph looks like a flat graph, but only two-dimensional. One-dimensional less for the graph. So the graph of this would be two-dimensional. The graph of this would be a plane in three-dimensional space put in there at some point. So the graph of such a thing looks like a linear object, one dimension less, a flat plane. So this is what equations, individual equations, look like. They have a geometry in Cartesian space. You can determine what space they all lie in by the dimension, by the number of variables that are used, and so on. So this is basically what I wanted to say about linear equations. Recognize them by their graph, flat, no curving. Recognize them by their equation, appropriate operations, and all the powers, all the exponents on the variables are 1, or they could be 0. And so now let's take a look at linear functions. And I have a little ditty about functions in general here, so if I write f r2 arrow r, this notation means something. It means that you have two domain variables, usually indicated x1 and x2. It means you have only one range variable. We could call it y1, but traditionally if there's only one, you just call it y. So this tells you that you have two domain variables and you have one range variable, and there's some equation involved. So for example, f of x1 and x2 could be x1 squared plus x2 squared minus 3. So this equation is involved, and this equation inherently means the range variable y is equal to x1 squared plus x2 squared plus 3. So it's pretty obvious y is the function that you've seen before. So that's the first piece of information. This equation gives you this equation involving the range variable and the domain variables. It also tells you the following fact. Y is a function of x1 and x2. This means that it satisfies the vertical line test, or for each ordered pair xy, x1, x2, there's only one y. So this notation here means you've got an equation, and that equation is a function. And mathematicians use these functions a lot, and we use them in linear algebra a lot. This function's not linear because of these 2's. So let's take a linear function of two variables, a linear function of two variables. So it's a function. It's going to have two variables, and it's going to be real valued, a real valued function of two variables. The values are real numbers. The variables are two variables. And so now I'd like to give that function an equation. Snow, would you like to do this?
Sure.
F of x1, x2 equals 3 x1 plus 2x2 plus 1. Yeah, there we go. So this is the equation. Y equals 3x1 plus 2x2 plus 1. Snow has already checked that this is a function, so that's why this notation is okay. I didn't really, well, yeah, I know, but it is a function, so we will deal with it. And now it's going to be graphed in 1, 2, 3-dimensional space. Traditionally, the x's are horizontal, and the output, or the y, is vertical. And now we want to graph this thing. The graph will be a linear object in one less dimension. So we have 3 dimensions here, 3 variables. This will be a linear object in just 2 dimensions. So this will be a linear object in 2 dimensions. It will be a plane. And we'd like to be able to place this plane and see what it looks like in 3-dimensional space. What does it look like? Well, it's got a slope in the x1 direction, and it's got a slope in the x2 direction, and it's got a translation term. So let's see if we can do that. To make matters easier, I'm going to change Snow's formula to have a -3. It'll make it easier to see. We'll start off with a flat plane. The x1, x2 plane goes through y equals 0. And now I will slope it -3 units in the x1 direction. Now the x1 direction is coming right out at you, so I'm going to slope it 3 units in that direction. If you are in an airplane, this is called pitch. And now I'm going to slope it in the x2 direction. Now the x2 direction is this direction. I'm going to slope it in that direction 2 units. So this is now the correct pitch and yaw of the graph, and now I have to move it up 1 unit. So beginning with a flat x1, x2 plane, we pitch it 3 units, -3 units in the x1 direction, pitch it 2 units, rise over run in the x2 direction, and translate it 1 unit up. So it's got an x slope in the x1, slope in the x2, translation. And that tells what the graph looks like in 3-dimensional space. So I'd like you to get a hang of that, what these numbers mean, the fact that these are slopes, the fact that this graph of this looks just exactly like the x1, x2 plane, geometrically identical, but it's got a pitch and a yaw, and it's been translated a little bit. So that's what I'd like you to know about how to graph functions, say from R2 to R. Let's take a brief excursion into higher dimensions. We could take a linear function from R3 to R. So L of x1, x2, x3, 3 domain variables, 1 range variable. L of this will be some formula involving x1, x2, x3, and eventually this will be equal to y. That's how functional notation works. So this could be 3x1 plus 2x2, let's add plus x3 plus 10. This graph will lie in 4-dimensional space because you have 3, this time 3 domain variables, and you have 1 range variable that's mutually perpendicular to those. Now, for those of us In linear algebra, it's a little hard to graph these things. This is a four-dimensional space. We are genetically bound to see things in 3 dimensions. But this is how it goes, and for my later evening class, they have no trouble seeing this 4-dimensional object. The graph of this looks identical to 3-dimensional space, to the x1, x2, x3 space. It looks identical, but it's been pitched with a slope of 3 in the x1 direction, 2 in the x2 direction, a slope of just 1 in the x3 direction, and it's raised 10 units up. That's what the graph looks like in 4-dimensional space. Now, the fact that we can't actually see it is not as important as being able to work with it. So we can work with these things algebraically, and our ability to, quote, see them diminishes as we get into higher dimensions. And even 4 dimensions, it's pretty hard to see what's going on. One final thing before we end this video about what's coming up in the course. And these things get a little more complicated than that. So we could have a linear function that maps 3-dimensional space into 2-dimensional space. How does it work? Well, we have 3 domain variables, and in this case, we have 2 range variables, y1 and y2. And this is a linear function. So let's see if we can write an appropriate formula here. Typically, the y's are in order placed in the range here. So the first entry here will be an entry for y1. It's what y1 will equal. And the second entry will be what y2 is equal to. So this could be something like x1 plus x2 plus x3 plus 4. That's a linear equation. And 3x1 plus 2x2 plus x3 plus 10. So such an equation will be a linear function mapping 3-dimensional space into 2-dimensional space. So we'll talk about these things. We'll be very interested in the ranges of such functions, the domains of such functions, and so on. So I think that's about it for this video. I will, on Friday, we'll have some worksheets where we'll put some of these down and talk about them, introduce the material for the following day. And I hope you have a good couple of days. Check out the Moodle site if you haven't seen it, and I will see you Friday morning.